So I'll just say a few words about this research. So Sam and I have been working on this topic for his dissertation. And now with the increasing large data volume and a complicated modeling, statistical computation is becoming more and more of a challenge. And even if you fit relatively simple model, just the sheer amount of data, and it's gonna make the computation much less efficient. And what he is trying to do is to come up with fast computational algorithm so that can fit basically all of the statistical models that we use today. And what he is showing today is a very small portion of that. And he is focusing on this particular technique called a Hamiltonian Monte Carlo. And so this is Bayesian model fitting, okay? I'll let Sam tell you more about it.
Thank you all, and thanks. Good morning, and thank you all for being here today. I'm really excited to talk about some of my research with Wanzhu and the software that we've been developing for the past couple of years. Before we get to the software itself, I wanted to talk a little bit about the statistics field in general and what statistics is all about. Essentially, statistics is about extracting information from data, and there are certain types of questions that we as statisticians seek to answer. One type of question is an estimation question. Can we estimate what the survival rate is of patients with a certain type of cancer? We seek to answer inference questions. Will a particular treatment be effective in increasing the lifespan of a certain population? And we also answer prediction questions down to the individual patient level. So will a particular patient respond to treatment or not? So all of these address the unknown. They're questions of the unknown, and statisticians agree that the answers to these questions are in the data. Now, because we all agree the answers are in the data, how we actually approach answering the unknown is very different depending on the statistician's paradigm or point of view. And currently there are two major schools of thought in statistics today, frequentist and Bayesian. So the frequentist school of thought is that the unknown can be characterized as a fixed quantity, and that the entire 100% of the information about the unknown is contained in the observed data. Bayesians have a little bit different approach. Bayesians view the unknown as a range of values that can be characterized as a probability distribution. We also use the observed data in order to estimate the unknown, but Bayesians also are able to incorporate any prior knowledge that we have. So as an example, if there's a study on the effectiveness of a particular treatment, Bayesians will use the observed data just like the frequentists, but may also incorporate prior information that may come from similar studies in the past. And these different views have a pretty dramatic effect on how the types of statisticians approach statistical computing and statistical modeling. So some of the appeals of the Bayesian approach, it's a very large topic, but some few key points that are relevant to my particular research and the software that we're working on. First of all, we can assign random parameters all the way down to the individual level. And this helps with more accurate predictions down at that level rather than relying on predictions at the population at large. And this approach works well or ties nicely into the precision medicine paradigm, which is interested in identifying the optimal treatment for a particular patient rather than just a cohort or a group of patients. So what's the right treatment for Mr. Smith, for example? Bayesian updating mechanisms are fairly straightforward to implement. They're used in a lot of machine learning algorithms. It's really a series of conditional probability statements used in simulation and a lot of machine learning software. Bayesians have the ability to incorporate information from prior studies, as I said before. And also, and finally, Bayesian methods have shown to be very effective in handling very high dimensional data sets and complex models, which is particularly important, as Wanzhu mentioned, in the environment today. So why another Bayesian software package? There's already a lot of Bayesian software packages available. What's the appeal or the What's the need for a new software package? Well, for one, big data, large data sets, lots of variables, the desire to extract as much information as possible to help people's lives and improve people's health. And standard Bayesian software was just not designed to handle the volume of data that we have today. And part of it is due to the hardware limitations that existed at the time a lot of this software was developed. So not so long ago, most computers had only one central processing unit or one CPU. So software that was designed to maximize or utilize that one processor 100% maximize the computational power of all the hardware that was available to them at the time. Now, fast forward a few years to today, almost every computer that you find today has at least 2 cores, at least 2 CPUs. Many have even 4 or 6 or more CPUs. We're also starting to do computation at the graphical processing unit, and many of the graphical cards have hundreds, if not thousands, of processing units. Not to mention, that's on just computers and laptops, not to mention servers. And the software, though, is written only to run on one processor at a time. So it's only using a small fraction of the power that we have available today. Some of the older Bayesian software has some limits in terms of model flexibility, and we wanted to design something that's user-friendly in a language that people use, statisticians and analysts use today. So we mentioned Bayesian statistics a couple times. What is Bayesian statistics? Where does it come from? The original theorem comes from Reverend Thomas Bayes, philosopher, Presbyterian minister, mathematician back in the 18th century. His theorem, called Bayes' theorem, now was published 2 years after his death in 1763. And the essential part of his formula is on the middle of this page here, where we have the posterior distribution is related to the likelihood times the prior. So as I mentioned before, Bayesians are interested in estimating the unknown. We can represent the unknown as a range of values, as a probability distribution. And our desire is to estimate this posterior distribution. That's the goal of Bayesian analysis largely. And here we have the 2 components that I mentioned that go into estimating the unknown. First of all, the likelihood. The likelihood is based on the observed data. Frequentists and Bayesians both rely on the likelihood of the observed data, and that the likelihood is multiplied by the prior, which is any prior information that the investigator may have or may know from prior studies. And the combination of the 2 forms the basis of the posterior. However, it doesn't give us the entire distribution of the posterior. We can't typically use calculus to derive the entire posterior distribution analytically. Because of that, we have to use other techniques to ascertain the posterior. And Monte Carlo simulation is one of the major techniques that Bayesian statisticians use to estimate the posterior. For those who may not have heard Monte Carlo simulation, it's based on randomness, just like coming from the gambling casino. So random numbers are used to generate values of the posterior, the information that we do know based on the likelihood and the prior. And when we aggregate all those samples together, paints us a picture of what the posterior probability distribution looks like that we're trying to analyze. And this Monte Carlo approach is not actually new. It's been around for a number of decades. One of the first methods, Monte Carlo simulation methods, was developed in the 50s for a statistical physics application called the Metropolis algorithm. It was used to model the collision of molecules. It was later extended in 1970 by Hastings, and now it's called the Metropolis-Hastings algorithm. Metropolis-Hastings is very flexible. However, it has some efficiency limitations. Gibbs is another Monte Carlo simulation technique. It's very efficient, but has some limits in flexibility due to mathematical restrictions in its application. Some of the advantages of Monte Carlo simulation are actually the theoretical support. There are very limited very few theoretical restrictions in designing a valid Monte Carlo simulation. The drawbacks and the challenges of Monte Carlo simulation for a long time have largely been computational. Just having the computational power to be able to generate enough samples to get an adequate representation of the posterior. And now that we have the computational hardware and we have some new algorithms that are available to us, like Hamiltonian Monte Carlo, I think we're able to break through some of these barriers. So Hamiltonian Monte Carlo is a newer Markov chain Monte Carlo technique. It's based on the Hamiltonian mechanics equations, the differential equations that originate in physics and are used to model the laws of motion. And those equations have actually roots in differential geometry. So there's quite a lot of theory that supports that supports this methodology. It's very flexible and efficient, and the essential innovation that Hamiltonian Monte Carlo has over other standard methods like Metropolis or Gibbs is that Hamiltonian Monte Carlo uses the gradient or the derivative of the log posterior to help guide the Monte Carlo simulation. And what that helps us do is, in high dimensional space, when there are a lot of parameters and a big data set, it helps to quickly guide the simulation into the region where we want to sample the posterior, need to sample the posterior most efficiently. So it works for large data sets with many variables, which is part of our impetus for designing this software. Now, a couple of key concepts about Hamiltonian Monte Carlo. Just like in any Bayesian analysis, we have a parameter of interest or multiple parameters of interest, which we can call theta. For each of these parameters of interest, we create an auxiliary or latent variable called p. P comes from physics. It's called momentum in the physics language, but it's just a latent variable in our application. And the joint space that's created by the Hamiltonian differential equations and the combination of the momentum and the variables of interest theta creates trajectories, a space of trajectories upon which we can run our simulation and get an estimate of what the posterior distribution looks like with the gradient of the log posterior guiding us along the way. So this is a visual of what the HMC algorithm does from more of an intuitive point of view. We have a picture here. We can imagine the horizontal axis would be theta, one parameter theta, our parameter of interest. We can, left side might be a low value of theta, right would be a high value of theta. The vertical axis would be the latent variable or P or momentum. And then this surface, which looks like an inverted bell curve, is created by a combination of the data and the Hamiltonian differential equations. And the way Hamiltonian Monte Carlo works is that this dot represents the current value in the Monte Carlo simulation chain. So we start off a simulation by applying some random force in a random direction, either positive or negative, some random force, maybe a light force or a heavy force. And this is considered a frictionless surface. So the ball will go back and forth until we stop the ball. Now, once we stop the ball, say at this subgraph D here, and say this where I have my cursor, I don't know if you can see it, this would be where the ball is, would be our sample value of theta. So we pick this, and this would be one of our samples for the posterior. And then we repeat the process all over again. Apply another random force to the ball. It goes back and forth. We pick another sample, so on and so forth, hundreds or even thousands of iterations. And as you can imagine, most of the samples are going to occur in the valley here, is sort of the peak of this inverted bell curve. But we will get samples out in the tails as well. So this is called an ergodic Markov chain. It's able to sample from the entire posterior distribution and give us a picture of what that looks like. Now, this is the procedure of the full HMC algorithm itself, and there's quite a lot here, so I won't have time to go through all the details, but a few key points. If you're familiar with the Metropolis-Hastings algorithm, you might notice that this looks very similar to Metropolis-Hastings. We have to specify n, or the number of samples that we need to take in the Monte Carlo simulation, and there's an outer for loop that governs how many simulations of theta that we want to pick to simulate our posterior. And then in the middle here is the innovation of Hamiltonian Monte Carlo. There's an inner loop called the leapfrog loop with a tuning parameter called L leapfrog steps. And the leapfrog function is shown here. It's actually a pretty simple function. And the purpose of the leapfrog function is to provide a discrete approximation of the solution to the Hamiltonian differential equations. And it's very simple, has some very strong mathematical properties. And because it's computationally very straightforward, it works well in a simulation like this one where we have to do a lot of gradient calculations. So here's the gradient appears a couple of times in this function. So we have n simulations and L leapfrog functions. So on the order of n times L gradient calculations. Now with that, let me show a short animation of Hamiltonian Monte Carlo compared to a standard Metropolis-Hastings simulation in progress for a linear regression application. And this is using the software that Wanzhu and I are developing. So on the top, we have the top two charts show the simulation for HMC. The bottom two charts show the Metropolis-Hastings simulation. The vertical axis in all of these charts shows the values of our parameter interest, which we're calling WIP, just based on the particular data set, ranges from -40 to +40. And what the trace plot is showing is the values of our sampled values of our parameter and the number of simulations. So both of these simulations we have 4,000 simulations in both of these algorithms. And both of these methods start at 0 for our initial estimate because we don't know what the true parameter value is. And Hamiltonian Monte Carlo and Metropolis-Hastings both have a random guess in terms of what the right direction is to do our sampling, and they both guess wrong initially. They both go away from the red line, which is where the true median estimate is. The Hamiltonian Monte Carlo actually goes up above 100, but quickly comes back down due to the contribution of the gradient to this red line region within 200 samples or so. And once it gets into this region, we sample right around this region and get a nice sample of the posterior density, which we show on this kind of flipped histogram over here on the right. So outside of these first initial couple samples, we have a nice representation of what the posterior distribution looks like. Metropolis-Hastings also starts off going in the opposite direction, makes its way down to the region where we need to do our sampling, but it's a little bit slower than Hamiltonian Monte Carlo because it's based on a random walk. It doesn't have the guidance of the gradient to move it. And so it moves more slowly and takes about 500 iterations to get down to the region of interest. And you can see that Metropolis-Hastings is starting to form the right histogram or the right posterior density, but it's going to take a number more samples and is less efficient than Hamiltonian Monte Carlo. So with that, let's move to our vision for developing this software. We want to make the Hamiltonian Monte Carlo algorithm and all its nice properties readily available to scientists, data analysts, statisticians, anyone who wants to use Bayesian software for data analysis. And we advocate Hamiltonian Monte Carlo particularly to do statistical computation for high dimensional problems, for very complex modeling. And to that end, we are working on 2 separate R packages to support this effort. We could have picked any language that we wanted. This algorithm is agnostic to language, but R is a popular language. I've used it myself for a number of years. A lot of people use it, so we settled on R for these 2 packages. My first package is called HMC R as a working name. Also have HMC Learn as another working name for this. Everything's written in R, so it will be open source. Everyone will be able to look at the code and look at the functions and see what it does. Very flexible software package. And the second package is designed to be a little bit more computationally performant. So it has R on the front end. So the user only needs to know R in order to run both of these software packages. But the second package uses Stan high performance software on the back end. And Stan is written in C++. It's a compiled language. It's very efficient in terms of running a lot of simulations very quickly, maximizes the use of multiple cores, and very powerful software. Now, we started off calling this semi-parametric regression, MCMC, because the original thrust of my thesis is on fitting semi-parametric models, which are high-dimensional models, have lots of variables, and are difficult to fit using software today. However, this software is actually being designed to fit a large class of models, including linear regression, generalized linear regression, including logistic Poisson models, mixed effect models, and even customized models. So with that, let me pivot to a bit of a demonstration of the software itself. If you're not familiar with the R language, maybe I'll zoom in a little bit. Hopefully that's a little bit more visible. So we have the R on the right. We have the script here on the left. And what I'm going to do is load my two packages, SemiPar MCMC and HMC Learn, as well as a few other packages to give us some data. Now I have about 5 examples here that I've already pre-run in the interest of time, but I've noted here how long each of these examples takes to run on this 2015 MacBook Pro. So this first example comes from the R-only package. It's a linear regression example using a data set from R. It uses, it calls a generic function called HMC, and some of the parameters that are used to input to this function include Y, which is the dependent variable, X, which is the design matrix or the independent variables, N number of samples, which we have 10,000 samples here. We have some initial values for our parameters where we start the Markov chain, some tuning parameters for HMC, and then functions for the linear posterior and the gradient of the linear posterior, which are shown here, in an optional parameter that that has the variable names. So after running this, which takes typically takes about 9 seconds or so on my on this computer, we have we can do a summary and show the quantiles of the posterior estimate after the 10,000 samples. So you might recognize this will be parameter from the illustration earlier, and here's the -16 median estimate, as well as the quantiles for the other parameters. We also have some graphics functions. We can plot, using the plot command, the histograms of the different parameters. So here's the histograms of the posterior estimates of each of these variables. We also have trace plots that are formed from this plot command. So we can look at the trace plots of each of these Hamiltonian Monte Carlo simulations, and they should also be what's called stationary. We're looking for relatively flat and bouncing on a certain median. That means it's a good simulation. Let's see. The next example is logistic regression. It's a little bit more complicated example. It takes 21 seconds to run. A lot of the same inputs, except this time we give it a logistic posterior and a logistic gradient function. Similar summary function of the quantiles of the posterior, and similar plots of the histogram and the trace plots. So that's the R-only package, and it's really appropriate for simpler models or for those learning HMC, but it can be generalized to really any model that you want to fit. This next, I want to show an example or two in the time I have remaining on semi-parametric regression, which is a bit more complex. This takes about 1.6 minutes to run. It's a semi-parametric regression where we're relating wage to marital status, education, year, and a non-parametric function on age, which has 20 knots. So the plot function after running this model, shows what the, excuse me, the different associations are for the independent variables. We see that having an advanced degree has a strong positive association with wages, college grad as well. And then here's the non-parametric portion for age. So when we start off our careers at 20, largely the mean wages tend to be at their low point, gradually increase to about 40, 50 years old, and tend to tail off towards 50s, 60s, and 70s. And we have credible intervals that are automatically plotted here in gray. And you can see wider credibility intervals on the right, since we have fewer data points with those who are working into their late 60s and 70s. This function also has trace plots as the other one does. One thing that I'll point out is that this software will actually runs 4 simulations all at the same time right now, and it uses all 4 cores of my CPU. So you can see that all of these chains overlap each other. That means that it's a good indication that we have a valid sample of the posterior estimates. I also have density plots, which are kind of a smoother version of the histograms, some specialized plots like autocorrelation to do some diagnosis. So I think maybe one final example real quick is, I'm just going to run this just so you can see it running. It only takes 10 seconds. Notice it's launching this on 4 different cores, and it takes about 10 seconds to run. And this is an example of modeling the best place to catch fish with a longitude and latitude map. And actually the plot takes longer to generate right now than the model itself. It'll show a contour plot here shortly of where the highest locations of fishing are. And we use the semi-parametric MC method to fit this. So here it is. So this contour here shows kind of the highest region. I think I'm pretty close to out of time, and I want to leave a couple of minutes for question. I don't know if we have time, but let me go ahead and stop there. Yes?
That's great work. In your ball, in the well example, how do you decide when to stop motion?
Right. There's in the standard HMC algorithm, we specify a parameter called L, which says the number of steps that we're going to take before we stop. And that's considered a tuning parameter. One way is just to specify that parameter up front, say 20. So after 20 steps, it'll stop every time. It's usually good to add some randomness to L so that we don't have a periodic chain. So there's a parameter to do that as well. And then there's some other algorithms that automatically pick that parameter for us in some other software. Yes?
How robust the local minimum maximum is this?
It's you know, like any other algorithm, it can struggle with local minimum and maximum, and there's active research and ways to kind of temper that. So that's, you know, that's one of the issues. You know, HMC works very well, but you know, if you're from multimodal distributions, you know, that's an active area of research that people are still investigating. And one's
Actually, this is, I think, comparing to the traditional MCMC like Metropolis Hastings, and particularly comparing to frequentist methods, this is a lot more robust in handling local and in handling local maximum values, because it has to, you have to think that that momentum variable is generated from a random process. So it's like kicking a ball. You could give it a big force and it will force ball to go very far. So, and that's not in a limited range. If you generate it from a Boltzmann distribution, which is similar to normal distribution, so you can cover the entire space. So technically, we should be able to, if you run the chain long enough, you should get to the global maximum.
Any other questions? All right, thank you very much.